we're going to talk a little bit about the interaction between light and matter and at the atomic scale. So what happens when an atom absorbs a packet of energy or a photon of light? What happens when an atom emits a photon of light? And it's meant to help us better understand spectra and what information is included in spectra then. So in this activity, we'll use a representation of the atom in which a central nucleus containing the protons and neutrons is surrounded by circles that represent the energy levels electrons can occupy. So I'm going to draw an atom including a nucleus and 5 energy levels that electrons could occupy. Use a dot to represent an electron at the lowest energy level. So first I'm going to make a nucleus, which is going to be the blue dot, the positive charges. And I need to draw in 5 energy levels. So not great at drawing perfect circles, but I will do what I can. So there's the ground state, first excited state, second excited state, third excited state, fourth. I'm trying to draw them so they're closer and closer. And I'm going to fail art-wise. So I've got 1, 2, 3, 4, 5. All right. And I'm going to put the electron in the lowest energy state. So that is this shell or orbital, if you're used to hearing those terms, that is closest to the nucleus. That is when it is most tightly bound to the nucleus, and that's the lowest energy. All right. One way an atom emits light, photons, occurs when an electron drops from a high energy level, also referred to as an excited state, to a lower energy level, and the lowest energy level is referred to as the ground state. So this would be the ground state, first excited state, second excited state, third excited state, fourth excited state. Will an atom emit light if all the atom's electrons are in the ground state? Explain your reasoning. And no. And there's no lower energy level. So this sounds like a simple idea, but it's actually really profound. The electron can only be at discrete distances away, and it can't be any closer than it is in the ground state. In which case does an atom emit more energy? Case A, an electron drops from the first excited state to the ground state, so from there to there. Or an electron drops from the third excited state to the ground state, which would be here to there. Well, there's a bigger change in energy in going from the third excited state to the ground state. Two students are talking about how light is emitted from atoms. Consider the following discussion between the two students and the sketches each student drew to illustrate their thinking. Student 1, I drew my atom like this because my professor said that the gap between the energy levels gets bigger and bigger as you go up in energy from the ground state. Student 2, I think you've got it backwards. The gap between energy levels will get smaller as you go up in energy levels, like I've drawn. And student 2 is correct. The spacing between energy levels becomes very, very small as you go to higher energy levels. So these essentially become circles that are just basically right on top of one another. You have a solid, glowing, hot object will emit light over the full range of wavelengths, resulting in a continuous spectrum. And your textbook refers to that as a thermal spectrum. If a diffuse and relatively cool cloud of gas is located between the glowing hot object and the observer, what type of spectrum will the observer detect coming out from the cloud? Now, this is what gives you an absorption line spectrum. So I've got my hot opaque source of light, and I've got a thin cloud, and I'm the observer over here. And so this thin cloud of gas is going to absorb whatever frequencies of light that it can, given what atoms it is made out of. And then those photons of light are re-emitted in random directions. So what I see coming along this path is going to be an absorption line spectrum with some discrete lines that are dark, the light that is missing. Alright. At right is a sketch showing one of the atoms in the diffuse cool cloud of gas described in the previous question. Note that the atom has several energy levels that an electron could exist in. Using a dot to represent an electron, a straight arrow to represent the motion of the electron, and a squiggly arrow to represent the photon, sketch what you think would happen within this atom to cause the type of spectrum described in the previous question. Explain the reasoning behind why you drew the electron and the arrow the way you did. So absorption means that there's going to be a photon of light coming in, and that energy is going to be absorbed by an electron. So the electron starts, say, in the ground state and goes to the first excited state. All right. Imagine that you're looking at a neon sign in a store window that says open. This sign can be thought of as a tube filled with a gas of neon atoms that have electrons changing from one energy state to a different energy state, and in the process are giving off mostly red light. Which type of spectrum would you observe coming from the open sign? Now that is an emission line spectrum. Electrons are going from a higher energy state to a lower energy state by emitting a photon of light. At right is a sketch showing one of the atoms in the neon sign describing the previous question. Note that the atom has several energy levels an electron could exist in. Using a dot to represent an electron, a straight arrow to represent the motion of the electron, and a squiggly arrow to represent the photon, sketch what you think would happen with this atom to cause the type of spectrum described in the previous question. Alright, so I have an electron in the neon atom in an excited state, going to a ground state, and in the process giving off a photon of energy. That's what creates an emission line. Consider the following discussion between the two students about the atoms and light coming from the red open sign from the previous question and the light coming from a yellow open sign that they see across the street. Student 1, I think that all you need to do to get signs to give off light of different colors is to use tinted glass of different colors. If you electrify a gas, white light is emitted, so the color of glass gives the sign its color. Doesn't sound entirely unreasonable. Student 2, this can't be it because the electrons will always move between the same energy levels for the atoms in a neon sign, and so they will mostly give off red light. I think that the yellow sign is filled with a different type of atoms with energy levels that are farther apart. So when the electron drops down from a higher energy level to a lower energy level, the atoms will give off yellow light instead of red light. To know it's shorter wavelength, more energy, higher frequency. So student 2 is correct. If I just have one kind of gas in there, it's going to give off an emission line spectrum, and that is not going to be white light. It's not a continuous or thermal spectrum. All right, redraw the initial drawing you made in question 1. I can't draw very well, so I'm going to defer, but you should have the greatest difference in distance between the circles for the lower energy levels and a smaller distance between the circles as you go to higher and higher energy Use the hypothetical atoms drawings A through F below to answer the next 5 questions. Note that there is only one correct choice for each question, and each choice is used only once. Which shows the absorption of violet light? So absorption means the electron goes to a higher energy level, and violet is the highest energy for visible light. So that's absorption, that's absorption, that's absorption. And out of those, the greatest energy difference is there. So that is D. Emission of blue light. So blue is on the high energy end of the visible spectrum, and emission means that the electron is dropping from a higher energy level to a lower energy level. So we have 2 cases of emission, and C is the case where it's going through a larger energy difference. So that is going to be blue. Absorption of green light. So green is longer wavelength than violet, so not as big an energy difference as we had for D. So let's look for an absorption that's sort of in the middle. This was our violet. This is a pretty small energy difference. This is a somewhat bigger energy difference between this and that. So absorption of green light would be B. Absorption of emission of orange light. So our ones that are emission are this one going down from second excited state to ground, which we said was blue, and this one, which has a smaller energy difference, so that could be the longer wavelength orange light, and which shows an electron being ejected from an atom. That is ionization. So you kick the electron out from one of the bound states, so it's free. And that's going to be A.